Another problem which is typically used to validate coupled geomechanics and flow simulators is the Mandel problem. And you can find it described in this reference. The solutions can also be found here. And the problem is really easy to describe. You're applying stress instantaneously at the top through a roller, meaning you allow displacement in this direction, but you don't allow displacement in this. So u in this direction, which is x, is 0. Same at the bottom, but you allow displacement in this direction, right? Then you allow fluid to flow out on both sides. And you can perform this experiment, compare the results with the analytical solution, and also compare that with your numerical simulator. One of the most common problems to validate coupled flow and geomechanics simulation. There are a couple issues you can have when modeling coupled flow and geomechanics. First thing is it's very computationally expensive when you try to do a fully coupled simulation. What do we mean by fully coupled geomechanics and flow simulation? It means that you're going to form one massive matrix of linear system of equations. So that equation, the matrix has the equation for flow, it has the equation for geomechanics all in one piece. You solve it together for both pressure and the displacements in all three directions if you're looking at a 3D simulation. So the problem grows very quickly when you have lots of gridlocks. There is the possibility of using some loose coupling between the geomechanics and flow, and that uses sequentially implicit approaches. But the problem is, depending on which of those approaches you're using, there is no guarantee of unconditional stability. So it's possible you choose an approach and your system of equations may not converge. So what do these approaches do? They basically will solve one problem first, then get the results from that problem and transfer that to the next problem. For instance, we solve the flow problem first, and we can solve it using Eclipse or CMG or your own in-house simulator. So you get the pressure solution after running the Eclipse model. Then you take that pressure, which is coming from the flow solution, and use that in the governing equation for geomechanics, right? Then you solve for displacement, and you can use abacus for that. And then when you get the displacement, you take the displacement solution, calculate the volumetric strain. Remember, the volumetric strain shows up in the flow equation. Then you solve the flow equation again for a new pressure, take the pressure into the geomechanics problem, solve for displacement, and then strain, take the strain into the flow problem, and you keep going until you have convergence. Then you move on to the next time step. So that's how we do loose coupling. And there are several approaches, four main approaches: fixed stress approach, fixed strain approach, then you have the drain splitting approach, and the undrained splitting approach. And of those four, the fixed stress approach is the most stable. Another point worth making is that most researchers and authors tend to use constant geomechanical parameters. So they assume one single fixed Young modulus, one single value for Poisson ratio, and they use that everywhere in the domain. And that's not really very meaningful, right? For the same reason, we don't use a single value of porosity, a single value of permeability everywhere in the domain for the flow problem. We shouldn't be able to use one constant elastic moduli for the geomechanical problem. Why? Because the rock materials are different, right? We talked about layering, different lithologies, different rock types. The different rocks will have different mechanical properties. And how do you get those properties? That's the whole purpose for our mechanical earth modeling. So from mechanical earth modeling, then you can have mechanical properties that vary in 3D space, and you're able to model the properties of your system more realistically. Here I'm discussing a model for how the fracture aperture, this is fracture aperture or fracture width, a modeling for how this aperture changes with time. And this, I actually implemented a model for this in the reservoir simulation result I had showed in the previous section. And why does the fracture aperture reduce? Because you build up stresses which are compressive, right, by the fracture surface, and they tend to close in on the propants. And typically we design these propants to be very hard, harder than the rock. So what happens if they are harder than the rock? They get embedded into the rock matrix. And as they get embedded, this aperture reduces. What if you design the propants to be weaker than the rock, right? They are not as stiff as the rock, then they crush. And you have propant crushing. Same deal, fracture aperture reduces. And this is the model I implemented for how the fracture width, which is called fracture aperture, how it changes with time. This is the elastic part, this is the viscoelastic part, controlled by this viscoelastic constant. And from this fracture width, we can estimate, or from the change in fracture width, we can estimate the change in fracture aperture. And fracture aperture times fracture permeability is your fracture conductivity. So as this fracture width reduces, fracture conductivity decreases, and that will affect your production. And I begin to show the results right here. So here are the stresses which are compressive. You build up these additional stresses due to loss in due to decline in pore pressure, and those lead to reduction in fracture width, fracture aperture right here. So it's decreasing from this value of 1 systematically to a value of about 0.7, 0.6. Then conductivity drops faster, right? Because it's a product of KF and WF, both of which are reducing, right? And that drops up to much less than 0.4. So a loss of about 60%, more than 60% of the original fracture conductivity. And what does this cause? It causes a reduction in your cumulative production. So if you assume your matrix permeability, fracture permeability is constant, meaning no change in fracture aperture, you have this black. Then at different values of the viscoelastic coefficient, which is what really drives the change in fracture aperture, because it's basically a model of creep, then you can lose up to about 35% of your cumulative production, which is very significant. And all of this is happening because your pore pressure is dropping, your effective stresses, which are compressive, are increasing, you're losing fracture conductivity because the fracture width is reducing, and then it translates directly to a loss in production. Those were cumulative production. Now we're looking at rates. And because it's log, that's one thing to watch out for. When you're using log, you can see this is logarithmic scales. Then it tends to mask the changes at late times and emphasize the changes at early time. And the changes are not significant at early time. Most of them are happening at late time, and you think the difference is not that much. Well, it's a lot, right? Because if you look at this is on the order of 1E10, but right here close to 1E2, so almost an order of magnitude bigger. And you saw this was precisely 35% when we looked at the cumulative production on the previous slide.